Hey, welcome to another episode of Stan Reads, where we walk through an interesting technical article together. Today we're going to be talking about how Turbopuffer built a distributed queue in a single JSON file on object storage. This article made the rounds a month ago. It got very popular on Twitter. It got 200k views, a lot of likes, and also had first place in Hacker News for a while, had top page there. So let's dive into the article. How to build a distributed queue in a single JSON file on object storage by Dan Harrison. So as Turbopuffer says here, and what Turbopuffer is, from what I understand, is they're simply a vector database on top of S3. So they're a very S3 native company, and they're part of this new trend of data infrastructure where the storage backend ends up being just S3 apart. Instead of using disk, they just use S3, and this is frequently used because of both cost efficiency. So S3 is a lot cheaper than hosting disks yourself on AWS or any cloud for that matter. And as well as simplicity, it's much simpler when object storage manages leader election for you, replication, and other hard distributed system problems. So here they explain how they built their internal indexing job queue on top of S3, and it's a very simple system. So I'm excited to walk through it today with you. I've got a lot of links here that we can open after and talk through. So yeah. We recently replaced our internal indexing job queue, which notifies indexing nodes to build and update search indexes after data is written to the write-ahead log. So as I said, they're a vector database and they have a write-ahead log. So whenever some data is written to the database and their write-ahead log, they have some asynchronous task that needs to notify their indexing nodes or their indexing EC2 instances to build and update their search indices. As I say, the queue is not part of the write path. It's purely a notification system used to schedule asynchronous indexing work. So this is what allows them to use a queue for this and what makes it so good. The prior version sharded queues across indexing nodes. So a slow node would block all jobs assigned to it, even if other nodes were idle. So the way I read this is all of their, let's say they had 10 indexing nodes, and each node had its own queue. So if one node was too slow in processing a single item, all the other items that are on top of its work queue would not get processed, obviously. And the other 9 nodes may be free, but since the items are on the queue of the node that is busy, that thing never got processed. So this is, I guess, something they wanted to fix with their prior version, basically sharing the workload across nodes. The new version uses a single queue file on object storage with a stateless broker for first in, first out execution, at least once guarantees, in a 10x lower tail latency versus our prior implementation. So indexing jobs spend less time in the queue. The 10x lower latency, I guess, comes exactly from this hot node or hot node problem. And as we can see here in their chart, this is actually an interactive graph. That's really cool. That's super awesome. The timing queue was something along the lines of 500 seconds on average, with some spike of up to 2,000 seconds even. And how much is 2,000 seconds? 2,000 divided by 60 is 30 minutes actually. So you had up to 30-minute queue in processing, and I guess this is after their deployment. The maximum was a minute, it feels like, for an item to spend in the queue until it gets processed. This would show the new queue at this time. Yep, that's pretty awesome. And their average was 500 seconds, which is, again, I guess like 5 minutes, 10 minutes actually. So quite the improvement from this, and it's a really good graph. We continue on. Why are we so obsessed with building on top of object storage? Because it's simple, predictable, easy to be on call for. I think that's a big thing. And extremely scalable. I think that one of the underappreciated aspects for building on top of S3, and what I really like in these data infra companies that build on top of S3, is that it really is operationally very simple. You're not on call for it, actually. The S3 team is on call for problems with S3, and that's very valuable. We know how it behaves, and as long as we design within those boundaries, we know how it will perform. Rather than present the final design of our new queue from the top down, let's build it from the bottom up, starting with the simplest thing that works and adding complexity as needed. So step 1, they start with a queue.json file. The total size of the data in a Turbopuffer job queue is small, well less than 1 gigabyte. I would expect that, you store data in a queue, something in terms of like, process this payload, or notify that this file got changed, etc. So I would expect it to be way less than 1 gigabyte queue jobs, or queues are generally very low throughput. This easily fits in memory. So the simplest functional design is a single file, like a queue.json, repeatedly overwritten with the full contents of the queue. So it's a little bit of a naive implementation. They just override the same file, but it does work. Then they have two components. A queue pusher reads the contents of the queue, appends a new job to the end, and writes it using compare and set operations. So the pusher is basically like a writer, the one who appends a new task to the queue. And because the way it works is they keep it all in a single file, obviously that pusher needs to download the whole file, modify it, and then return it back. And they use a compare and set operation, which is an S3 feature that got released in 2024. S3 basically offers something along the lines of versioning of files called an ETAG of an object, where you can basically say something along the lines of, put this object in S3 if the version matches what I expect it to be. And this gives you serializability of the file content, because if the ETAG had changed or if the version changed, you know that what you're writing is not the same as what you were expecting to write on top of. And that gives you the serializability. A queue worker then similarly uses the compare and set operation to mark the first unclaimed job as in progress, and then gets to work. So again, what this worker has to do is it has to download, again, the whole file, find the job it's going to take, mark it as in progress, and then write back to the object, so that everybody else who reads the object again knows that that thing is in progress. So they call pushers and workers clients, and the push and claim operations requests. The compare and set primitive makes this atomic. The write only succeeds if queue.json hasn't changed since it was read. If it has changed, the client reads the new contents and tries again. This gives strong consistency guarantees without complex locking. So again, if you download the queues.json file, and it looks like this with version 1, and you modify it, and let's say you modify this item to be in progress, if when you try to write it back, a version 2 has been written, you will fail that write and you will download it again, and this time you will download it with the version 2 changes, and then you will try to modify it again. So that gives you, that avoids ghost reads, and that avoids the problems of concurrency. This simplest of queues works surprisingly well. For up to 1 request per second, a limit imposed by Google Cloud Storage, or Google's S3, it's already production grade thanks to everything that object storage does for us. But most queues, including ours, receive more than 1 request per second. We need more throughput, so let's see how they solve that. But it seems like GCS has a limit on how many times you can modify a single object. Here they say, note that there is a once per second limit for rapidly replacing the same object. So replacing is the way of updating an object in S3. So in GCS, you can't modify this queue more than once a second. So if you have this naive implementation, which is just like a client directly working on top of S3, you can only change it once per second, which is obviously nothing. I try to create an ASCII chart here for the whole thing. So again, the pusher saves the new jobs that have to be done, and the worker marks them in progress and reads them. And I tried to create a more detailed JSON. So let's imagine we have a queue.json with a jobs array, and the array has different jobs with different IDs, and they have a status. So pending means this empty circle, and in progress means this half-filled circle here. So what the worker does, what the pusher actually does first, is it first gets the queues.json, so it reads the current state, or it potentially has it in memory. Then it appends a new job, so let's say this new E5 job, and then it says, okay, put this if it matches with V2, I guess. I think I got this wrong in the opposite order, so let's start again. The worker here gets the queue.json, reads it, and then marks the first item as being in progress. So it claims that item and it starts working on it, whatever the job is. Here in the Turbopuffer example, the job would be doing some sort of indexing work, right? And then, because it wants to persist the fact that this is in progress now, it issues a put with if match. It says, okay, modify this job subject to contain the in progress value if the ETAG matches. And if it matches, then great. If it doesn't, then it has to retry, it has to reread everything and basically restart the whole thing again. And then the pusher can do the same thing by appending a new job. and again, it reads it. It depends on your job, and tries to put it with an updated e-tag. And that's really how it works. It's very simple, honestly, and that ensures the serializability of everything. But again, as I said, this has issues. You can only do one request a second on GCS, and even in S3, you're still sort of limited by the amount of writes you can do a second. I think S3, usual put in S3, the P99 is probably up to 100 milliseconds, 200 milliseconds. So you'll find that you'll be hard pressed to do more than 5 to 10 requests a second with this. Plus, you would have a lot of contention. If you have, let's say, 10 pusher clients that are always pushing new data, this step will frequently fail. So you need something to streamline all of those operations. So then we get to step 2. Step 2 uses a so-called group commit. Object storage has many virtues, but low write latency is not one of them. Replacing a file can take up to 200 milliseconds. So instead of writing jobs one by one, we need to batch them. Whenever a write is in flight, we buffer incoming requests in memory. As soon as the write finishes, we flush the buffer as the next compare and set write. This technique is commonly called group commit, and is the same pattern Turbopuffer uses to batch their own writes to the write-ahead lock. Traditional databases also use this technique to coalesce fsync calls to maximize the committed throughput to disk. Now, this is relatively very simple. It's the same as before, but instead of naively writing to the S3 file on every possible change, you buffer it. While you know that you have your previous write in flight, you buffer it, and you buffer, and when the previous write comes back, then you write the new one. So this eliminates contention of in-flight requests, is how I understand them. Group commit solves our throughput problem by decoupling the write rate from the request rate. So the write rate, if I understand, is the rate you write to S3, and the request rate is the rate of new items coming in or items being taken to be in progress. The scaling bottleneck shifts from the write latency to the network bandwidth, far greater than what Turbopuffer needs to track the indexing jobs. The network bandwidth here is like how much can you commit to S3 per write, is what I understand. However, there's still a problem. In any Turbopuffer region, tens or hundreds of clients will contend over the single queue object as a new data is written to many namespaces. Tens or hundreds of clients will contend over the single queue object. So again, if we have tens of workers, tens of pushers, and they all have their buffer, they're still contending. Even if a single worker doesn't contend with itself by, sending 5 requests a second itself, there's going to be another worker that probably sends requests. Since compare and set ensures strong consistency by forcing each write to be non-overlapping in time, obviously, because if it's overlapping, then you would get a conflict on the e-tag. We can only fit 1 divided by 200 milliseconds, meaning around 5 writes a second, and we still have the 1 request per second limit on Google. The problem is no longer the throughput, they just need fewer writers. And they note here that this design, coupled with sharding to the local queues, is roughly what they had in production prior to this update, so we'll get back to this. The next section describes Turbopuffer's current production indexing queue. So they had something like this, from what I understand, which was 1 queue per one worker node. And the pushers, I guess, buffered to S3. They wrote to S3, and the worker node would download from that S3 queues.json, which would be, worker queue 1.json. Let me go to step 2 here. I have it charted as well. So now we have the group commit. In the group commit, as you can see, the worker is the same as before, but this time it has a local buffer in memory where it accumulates all of the claimed jobs it wants to claim, while the compare and set operation is in flight to S3. So it's already sent a request, and it's waiting on S3 to reply. And while it's waiting, it's buffering the rest in memory for its next request. And the same thing happens with the pusher if it wants to write new stuff. It knows that if it has a write that's in flight and hasn't received a response yet, it's going to buffer it in memory and then push again. So this reduces the contention. Imagine all of these were sent like every 10 milliseconds versus waiting 200 milliseconds to write like 10 or 20 at once. So that should definitely help. Here we have a timeline. At T0, we get queue.json. We get that e-tag is equal to 7. At T0 to 200, the requests arrive and are buffered locally. And at T200, we get a put. We put a put to save all the requests that we had up until the buffer time. and the object now becomes a v0 tag. Then we flush the local buffer as well when we start collecting the new batch, and then we get, obviously we load the new queues.json and we buffer again and we buffer and buffer until whatever the timeout passes or there's a request in flight, and then we put again. And yeah, this basically increases the amount of jobs you can write per second while keeping the write rate basically the same per second. So it's just batching, really. So now we get to what they changed and what this article is about. Step 3 is about queue.json with a brokered group commit. And a brokered group commit here literally means add a layer of indirection here. So instead of having each client directly talk to S3, just add one big node here called a broker. To eliminate contention over the queue object, we introduce a stateless broker, which is responsible for all interactions with object storage. So stateless here is important because that makes it very simple to operate. Our clients must now talk with the broker instead of writing to object storage directly. This broker runs a single group commit loop, i.e. a single batching sort of process, on behalf of all clients. So no one contends for the object. Critically, it does not acknowledge a write until the group commit has landed in object storage. No client moves on until its data is durably committed. This is also important, but it's very simple. So this time we have, well, let's continue. Now the broker is the bottleneck, but a single broker process can serve hundreds or thousands of clients without breaking a sweat because the writes are so small. It's just holding open connections and buffering requests in memory while waiting on I/O. Object storage does the heavy lifting. And again, we have a single broker instance here, which keeps the buffer in memory of stuff that has changed to be in progress and new stuff that has yet to be written. And then all the clients just keep open connections to that one broker, and they write their little requests with a few items. Let's say the worker says, claim that object 1 is in progress. Pusher says add, object or job number 12, etc. So they should be very simple and lightweight requests for the broker to just keep. And the broker pulls all of these requests and responds only when it manages to commit to S3. So the broker does the batching, and after a certain time period passes, it writes to S3 and it saves the new data in S3 and responds only when all that is done. And then when the workers and pushers or the clients get a response, they know that their work or the request has been durably committed to S3. And that's very simple. I mean, this broker doesn't have to be stateful at all. It can you can just spin up a new node, and it's going to read the queues.json. It's going to know what the state is. It just gets the state from S3. And that's it for scaling. The system can now handle Turbopuffer's indexing traffic, but we need high availability. So the reason they can handle the traffic now is because you did even one layer of batching above. So before you did batching on the level of the client, i.e. a client would not send one request to S3 per item. It would send, let's say, one request to S3 per 5 items. And now you have an aggregate S3 batching, which is to say 10 clients would not send 10 requests to S3. They will send 10 requests to a broker, and the broker will send one request to S3. So that scales very well. And then because the throughput is the limit, as they said here, which was 10 gigabytes a second, I think, of S3 throughput, however they claim that number here, then this broker can literally do 10 gigabytes a second to S3 all with one request or 5 requests, let's say, in theory. So the throughput is never an issue now. And the requests per second were offloaded to a broker instance instead of S3. So that works really well. Let's go over my diagram as well, in case it's useful. Starting from the bottom. So we have the many workers that connect to the broker, which is again a completely new EC2 instance. It holds the E tag in memory, so it should not have any contention with this because it's the only writer. So let's say in time equals 1, it wrote to S3, and it knows what it wrote, so it keeps it in memory. And in time equals 2, it writes again to S3, and it knows what the previous state was because it's the one who wrote it. So in the happy path, when there are no failures, there should be no contention here. And in the group commit buffer, again, everything is in memory and requests accumulate while there's a write in flight. And when the write completes, the entire buffer gets flushed again as the next write. And that's really how it works. And the clients only get a response when the write is successful. So if, let's say, this fails for whatever reason, the clients would know that their request was not successful and they should retry. they should retry by sending the same request to the broker. Continuing on, the step 4. So step 4 is, and also by the way, the difference here again, as they said, was they had one queue per worker node, and what they've done now is they have batched all of that into a single broker. So the real difference here from their previous design and this one is they introduced, well, first they introduced a single file, and then they added a layer of intermediation called the broker, basically an EC2 instance that runs some sort of code. On step 4, they say queue.json with an HA brokered group commit, so a highly available brokered group commit. The broker's machine might die at any time, true. Similarly, some workers might claim a job and then never finish it, true as well. So these are the two failure cases you really need to guard against. What happens with this design if the broker dies? Well, a new broker needs to come back up. But how do the clients figure out what the broker IP is? How do they do the service discovery? That's something that hasn't been solved yet in this design. And the other thing is, if a worker becomes dead or becomes a zombie and stops replying, how do you eventually free up a stuck job from that worker and give it to some other worker? Because, again, if a job gets stuck in one worker and the worker doesn't reply, and that job gets sort of held hostage by that worker for a very long time, potentially forever, you would not be able to solve this until you somehow, kill the worker or free the task. So you need some automated way to solve these sort of tail latencies when a worker dies. In queues, this is done with leases. So the queue broker itself, which not this broker, but let's say a RabbitMQ would see that, okay, this lease hasn't moved in, let's say, 30 seconds. They haven't acknowledged that this has been completed. So let's treat it as abandoned. Or you could do heartbeats, which is what these people will do here. But you need some sort of liveness check to say, hey, if you don't complete this job in 1 minute, I'm going to give it to somebody else. Or if you are still completing the job, let me know that you are alive and you're making progress on it. Otherwise, the broker has no way to know, are you dead? Are you just stuck? What's happening? And should I give it to somebody else? And here is the fix. The fix for each of these has the same shape. You have to notice when something is gone and hand off the responsibilities. That's very easier said than done, but the details differ. If any request from a client to the broker takes too long, we start a new broker. So this is their health check for the broker. If any request from the client to the broker takes too long, this basically is saying if the broker is taking too long to respond to a request, they kill the old broker and they start a new one. Clients will need a way to find the new broker, so we write the broker's address to queue.json. I really like this. So the service discovery happens inside queue.json directly. So it tends to become both a place for metadata and for data. The data being your jobs and the metadata being the broker IP. So I guess there's some logic here where if a client sees the broker is taking too long to respond, the client starts a new broker or issues a request or something to start a new broker. We'll go over that in a second. I can share what they said here. They did share on Twitter how they did it. Somebody asked them, if any request from a client to the broker takes too long, we start a new broker. What starts the broker? That's a very good question. And the author says, for operational simplicity, they co-locate the broker on one of the query nodes. I guess this means the client node. So the broker is really living... The broker is probably living on some of these clients' EC2 instance. And because it's living on the same EC2 instance, the worker or the pusher can really easily talk to it. We've tried letting the client start it and also a background loop. Both work fine. So I guess this is it. We let the client start it, I guess assumes that if any of these clients figures out that the broker is taking too long to respond, they try to start a new one on their local process, or they kill the one they have. Or a background loop, from what I understand, the background loop would be, I guess, some loop that sort of continuously asks the broker, are you alive, health check. And the moment it figures that it's dead, it kills it and it creates a new one. And on startup, all of these brokers most probably race to get to the S3 object and they try to register their IP here with a new E tag. So on failure, if every client tries to create a new object, a new broker, then you might get a lot of racing. You might get, let's say, we have 6 clients here, and if all 6 try to create a new broker, then you would get 6 new brokers created. Each broker will try to race each other to override this, and I guess the last broker that manages to overwrite it basically takes it. Because again, if the broker, let's say if broker 1 registers ETAG 100 and then it tries to write and it sees that ETAG has moved to 101, that tells the broker that, hey, there's somebody else that registered ETAG 101 and is newer than me, so I should give up. So that stops all 6 brokers from living forever. I guess they have like a self-destroy loop, or sorry, self-destroy check. But it's funny how you immediately get into like complex distributed system details when you have to solve the problem of distributed leader election, right? So that is interesting. So clients will need to find a way to find the new broker, and we write the broker's address. The broker is stateless, so it's easy and inexpensive to move. Of course, the broker just starts up, it reads the S3 object, and it's done. It's ready to serve. What happens if we end up with more than one broker at a time, which is what I was asking? Well, that's fine. The compare and set operations ensure correctness even with 2 brokers. The previous broker eventually discovers that it's no longer the broker when it gets a compare and set failure on Q.JSON. So the thing I was saying here, if it has an ETAG of 100 and it tries to write with that assumption in mind and it finds a newer ETAG exists, it should assume that, okay, there's some other broker that's taken hold of the object and I'm no longer the most recent one, so it can just self-destroy, it can shut down. The only downside is a bit of contention and thus slowness for this brief duration. Again, as I was saying, if every client tries to create a new broker, you get a lot of contention because you get 6 brokers here that are trying to race for it at the same time. So let's see if this gets addressed. If not, I'll have to ask them on Twitter what they did with this. Should probably use a better color for this. Let's go with purple. Okay, for the job claims, now we're moving on to the job claims, which is what happens if a client fails as they have claimed something and they're working on it and they never mark it as completed. How do you know that the client has failed and when do you decide to move the job away from that client? For the job claims, we add a heartbeat. Periodically, the worker will confirm that it's still on track by sending the broker a timestamp, which is then written to Q.JSON for that job. 1 heartbeat per claimed job. And again, this is mixing metadata with data. The heartbeat is metadata of the worker that's working on this job. And as you can see here, the jobs have it. The job has the ID of the job, the status of the job, the worker that it was assigned to, this is metadata, and the last heartbeat of that worker. So what the broker can do here is it can check the last heartbeat timestamp, and if it figures that a heartbeat was too old, it can mark that task as dead, or basically reclaim it, give it to somebody else. The broker then buffers all of the requests in memory. So if it gets a claim request which says mark a job as in progress, if it gets a push request which is write a new job, or it gets a heartbeat request for that matter, it just buffers all of that in memory, and in memory writes the new JSON file, and when it's ready, it tries to commit the whole thing. So this is again very handy and a very cool way of working with it. If the last heartbeat for a job in the queue is ever more than some timeout, we assume the original worker is gone and the next worker takes over where it left off. This is again at least once, because you can still have duplicate processing with this, because if the worker let's say the worker heartbeats, its heartbeat thread gets stuck or something, it might still be processing it. So there are edge cases where the worker you thought was dead finished processing the job and a new worker also got the new job and it also processed it. So that's why you can have at least once. You can have duplicate processing, basically. And yeah, we have a graph that's really the same as the one I have here, I think. But I think this is their final design. This is their final design, and it's still very simple. You can capture it in just one markdown. I think this is pretty simple. I'm fairly sure Claude can one-shot this if I ask it to build it. And I'm pretty sure it doesn't take more than an hour or two to build yourself manually, the old school way, if you want to. And the last one, ship it. We built a reliable distributed job queue with just a single file on object storage and a handful of stateless processes. It easily handles our throughput, guarantees at least once delivery, and fails over 20 nodes as needed. Those familiar with Turbopuffer's core architecture will see the parallels. Object storage offers few but powerful primitives. Once you learn how they behave, you can wield them to build resilient, performant, and highly scalable distributed systems with what's already there. And Turbopuffer is a fast search engine that hosts trillions of documents, handles millions of writes, and serves 10K plus queries. a second. So this is the article. Again, it's pretty interesting, pretty fun how they built such a, I wouldn't say complicated system. I mean, it's a simple system, but it's complicated in how easy it is, I guess I would say. It's just really awesome. People would download entire queues for this, like RabbitMQ, or even Kafka now has a queue feature. But goes to show you can write this like pretty easily with S3, and it's much easier to manage because, again, you almost have no code to manage. All the code is in S3. One thing I'm disappointed about is why didn't they open source this? I messaged them when they released this. I asked them if they should open source this. It's so simple, and I think it will become a pretty popular library if they did. But they haven't open sourced it, and I haven't yet seen any sort of good open source implementation. So let's go through the rest of the links I have. We went to how they restarted. And oh yeah, that's right. We had to ask them a question. So what I'm wondering here is, does the background loop have some sort of health check? And where does the background loop run? So is it running on every client, or is it just running on the node with the broker? And the other thing I'm kind of wondering is, if you let every client start it, does that imply that every client creates their own broker node locally? So let's see. Few questions I'll ask. If every client, I'll also ask which one did you settle with. If every client starts it, does that imply that for a not for a sub-second, but for some time, you get a broker node running on each client contending with each other, and only the last one to register wins, by virtue of the other ones self-terminating gracefully. And then the other question would be, for the background loop, does it also perform some sort of health check on the broker? Where does it start the new broker? Is it, in other words, i.e., is it a loop that runs on every client, or on just one node, the broker one? And let's add a bonus question, bonus Q. Why don't you open source this? It will become a popular library. Cheeky smile. Okay, let's see what they say later. So I also had some comments from the Hacker News thing. So they say here, the original graph appears to show the blocking issue of the previous synchronization. 10 minutes to process an item down to 6. Any central system would seem to resolve this for them. I didn't exactly get this. I guess they're talking about the original graph. I don't think it went, whatever. I don't think it went down to 6 minutes. It went down to a minute. So it was a lot more and went down to a minute. So I think this is wrong. In any case, in any organization, it's good to make choices for simplicity rather than small optimizations. You're optimizing maintenance, incident resolution, and development. And I think this is a big thing that people don't take into account. Whenever you see people talking about systems, they talk about how much they optimize it, what sort of big numbers it supports, what the latency is, what the throughput is. But nobody says, this system has not caused a single on-call incident for the last 6 months. Nobody says that because that's not public information. If somebody is drowning in incidents and they have, let's say, an incident every day, they would never share it. So it's one of these things that companies just don't share, because I believe most companies are broken inside. Like, I think a lot of companies just deal with awful incidents very often, and it's really rare to find a very reliable sort of platform or infrastructure. So it's something we as a community don't talk openly enough about. And yeah, but it's extremely important. And optimizing for simplicity, meaning that things that don't break and that make incident resolution easy and make development easy, I think is very important, and people aren't taking that into account enough. And that's why we have trends like the Just Use Postgres movement, or this S3. I mean, this trend of building data structures or data infra on top of S3 is part of the same thing. It's optimizing for maintenance, less incidents, and developing something easier, having an easier API to work with, not having to worry about all sorts of distributed system problems. So the user here says, typically I have a small Postgres server for these things. It will work out slightly more expensive than this setup for the action of queuing. Yet it would cope with so much more. It extends to all kinds of other queues in config management and with simple management, off-the-shelf diagnostics, and etc. Again, just use Postgres. If you have Postgres, you probably know how to manage it. A lot of companies manage Postgres. It has all sorts of diagnostic tools and etc. If you use this thing, you still have to build the metrics system for this. So you have to build some metrics inside this broker. You have to build logs. You have to build out metrics for the workers and the pushers as well to probably have some information about that. And there's a lot of operational stuff that needs to get built around. Even as simple as on a system as simple as this one, you still need to spend effort to make it operationally nice to work with. And something like Postgres already comes with this out of the box. There's the PGMQ. Postgres message queue, I think, is a library, very popular library. That's just perfect for this. It's probably the best way to use queues on Postgres, and it's a very popular one. I mean, look, we have 4.6k stars here. So if you have Postgres, I would just recommend use Postgres, and you'll see why Turbopuffer did not use Postgres here. And as this user says, while the object store is neat, there is a confluence of factors which make it great and simple for this workload that may or may not extend to others. 200 millisecond latency is a lot for other workloads, and 5 gigabytes a second doesn't leave a lot of headroom, etc. And I don't want to be asked to diagnose transient issues with this. So I guess the person does not want to go on call for this S3 solution. Although I think it should be pretty easy to go on call for, again, this broker and this pusher client. I can't see it being more than a few hundred lines of code. So anyway, the user is Torn. It's simple to deploy and configure from a fresh deployment point of view, yet it would not be accepted into any deployment I have worked on. Well, obviously, if you have Postgres, there's no reason to introduce yet another system. Again, this is a very nice and simple system, but there's also something to be said about system sprawl in a modern infrastructure, company infrastructure. You don't want to have, as an extreme example, you wouldn't want to have 10 of these systems, all very simple in their own, but imagine having 10 different ones. That's a lot of things to juggle in your mind. So if a single Postgres can do all of this instead of custom-made code, that's what people would prefer. Or what also a lot of people prefer is to just, of course, use a managed service. And in a managed service, you don't need to deal with any of this, and you're paying somebody else to do it for you. But the reason Turbopuffer doesn't use this is because they don't have a Postgres. That's why. So as a user here says, depending on who hosts your object storage, this seems like it could get much more expensive than using a queue table in your database. And that's true. One thing that's not accounted for here is that all of these puts to the queue.json, every put costs something and every get costs something as well. Whereas if you have your own Postgres database, every request is essentially free because you don't pay per request, you just manage it. And the founder here says, we don't have a relational database. Otherwise, that would work great for a queue. So they themselves admit that using Postgres is really just good enough here. But for whatever reason, they do not have a relational database, which I'm really surprised by. I mean, I wonder how they manage all of the metadata and control plane operations for their product without a database, but whatever. They don't have a relational database. Maybe they have a NoSQL database. I don't know. You can imagine us continuing to iterate here to step 5, step 6, step n over time. The trade-off of each step is complexity, and complexity has to be deserved. This is working exceptionally well currently. Now, I love this quote, and somebody else here also talked about it, but this is just such a good quote. I will hang it here on my wall. The trade-off of each step is complexity, and complexity has to be deserved. People have to remember this. Don't introduce complexity in your systems, in your code, and your infrastructure unless it's deserved. That's why I see people adopt Kafka, and Kafka is just the canary in the coal mine here, but I see people adopt big data systems all the time without deserving the complexity. They just fall for whatever marketing they see, and they think, okay, this is the right tool for the job, so let me adopt it. In the same way here, you could see, you would say, okay, something like a RabbitMQ is the perfect tool for a queue job, for the job here of a queue, so let's adopt RabbitMQ. But RabbitMQ comes with a lot of extra complexity. And unless you deserve the complexity, you don't need to deploy something as complex as a big system like RabbitMQ. Again, if you just need a single JSON file here, so don't overcomplicate things you don't need to. It is a makes total sense for your use case. I have got bitten by using object storage as a database before, so that would depend on the pricing and busyness of the queue of the provider. Using whatever you have available instead of introducing complexity is the way. SQLite and Postgres goes a long way for use cases you would not originally think would go well with a relational database too. Full text search, using it as a queue, and also using it as a Kafka, by the way. I have this project I really love called Tansu, which implements Kafka on top of Postgres or SQLite, and it works very well. But that's a topic for another show. Again, they say here, the founder says that due to the batching, this doesn't really consume a lot of requests at all. Class B is a type of request in S3, so the requests cost, let's say, $5 a million requests, and this only consumes a few million Class B requests per month, so let's say it costs like $10, $20 a month, which is again nothing. And yeah, another person who says here they love the approach of the trade-off of each step is complexity, and complexity has to be deserved, so that's awesome. What else do we have here? The usual path an engineer takes is to take a complex and slow system and re-engineer it into something simple, fast, and wrong. So wrong is the key word here. But as far as I can tell from the description in the blog though, it actually works at scale. This feels like a free lunch, and I'm wondering what the trade-off is. And here's a little bit more discussion of how this works. So they say it seems like the approach that trades off scale and performance for operational simplicity is an important one. It does trade off scale and performance for operational simplicity. The performance is slower, as we said, 200 milliseconds for a queued job to get queued. I mean, with RabbitMQ it would probably take a few milliseconds. And the scale is a bit limited, I would assume, but even then I think with the brokered commit they get pretty far with it. They say they only have 1 gigabyte of records and they can use a single committer to handle all requests. Failover happens by missing a compare set, so there's presumably a second of latency to become leader. Yeah, this is a big thing. During failover, the failover is the weak part of this design. During failover, as we said, if we create many different brokers, they all try to contend to each other, and this causes more than a second of latency, I believe, or maybe up to a second actually. And the workers and the clients then need to retry, because imagine the following: you create broker 1 and it registers here as the newest broker, and it starts accumulating requests in its buffer, and let's say 900 milliseconds pass, and the 1 second it starts to commit. It tries to commit, but then it finds out that there was a newer broker that came in with version 2 and that this is no longer the active broker. So what does the broker that just sent the request do? Oh, it fails. It rejects all the requests and it terminates, and then the clients need to reconnect to the newest broker again and commit again. So this is basically the failover part, and that's why it's a little slower than it ought to be. This is not to say it's a bad system, but it's very precisely tailored for their needs. If you look at the original Kafka implementation, for instance, it was also very simple and targeted. I wouldn't really agree with that. As you bolt on more use cases and features, you lose the simplicity to try and become all things to all people. I would not say that Kafka did this, by the way. Kafka has always been a lock, and if anything, it got simpler because it removed Zookeeper, it removed clients connecting to Zookeeper. Yeah, it added exactly once, which was transactions, so maybe that's a little bit of complexity, but it really doesn't hurt your write path. I mean, it doesn't hurt your main path to using Kafka. So in any case, but it's true that, systems get more complex as you add text to them. And the author of the piece here agrees. Given that Turbopuffer itself is built on the idea of object storage plus stateless cache, we're all very comfortable dealing with it operationally. So they're S3 experts, these guys. This design is enough for our needs, and it's much easier to be on call for than adding an entirely new dependency would have been. And that's true. I mean, if they had to add RabbitMQ or some sort of queue thing, or even a Kafka, which would have been way overkill here, they have to learn a brand new system. Whereas if they're comfortable with S3, and again, they can write a few hundred lines of code, it's very nice. It's much easier. In my opinion, this is the ideal way to engineer most, but not all systems. As simple as your needs allow. Nice work. Nice work, guys. So here somebody explains how the failover happens, and it's similar to what I tried to explain. So conceptually, the failover makes sense. How complicated is it to implement this failover in a safe way? If there are two processes competing for compare and set wins, i.e. the wins of who's going to write the latest broker IP here, is there not a risk that both will think they're non-leaders and terminate themselves? And it's a good question. When I thought through it, I think there is no such risk, and this user normal Gaussian here replies in the same way. The broker lifecycle is presumably, it starts, it loads the queue JSON from the object storage. It starts receiving requests. I think this is wrong. It would load the queue JSON, and then it needs to write the queue JSON with its IP here. So I think this path step 2.5 should be, it writes the IP of the broker. Then it starts receiving requests from clients. I mean, clients in parallel, they also read this and they discover the IP and they connect to the broker and they start writing. So it starts receiving requests. It edits the in-memory JSON with the batch data. And on 4, it saves the data with the compare and set. And on failure, that's not due to compare and set, but some other failure. It either recovers or fails. This doesn't really matter here. And on success, of course, it succeeds all the requests and continues receiving requests, so it empties the buffer. And 7, on failure due to compare and set, which means basically you get a new E-tag version here that's invalid. You fail all the active requests and terminate. So the client should have a retry mechanism against the broker in case your active request got failed and the broker terminated. You have to reread the queue again and try to find a new broker, which may include looking up the address again. It should include that. From the broker's point of view, it will never fail a compare and set until another broker wins a compare and set again, because it's only one broker, one instance here that's reading and writing this thing. So the moment it fails with an E-tag error, it knows, okay, there must be some other broker somewhere here that's writing to the queue.json. And I'll just terminate myself because somebody else owns it now. At which point that other broker is the leader. If it does fail a compare and set, the client will retry with another broker, which will presumably or probably be the leader. The key insight is that the broker reads the file once. It doesn't compete to become leader by rereading the data, and this is okay because of the nature of the data. You could also say that brokers are set up to consider themselves maybe the leader until they find out they're not, and losing leadership doesn't lose data. It doesn't lose data because they haven't confirmed or responded to the requests here. So basically a broker treats all of this commit buffer data as ephemeral, meaning something you can lose, until the put succeeds. And if it fails, they say, okay, my ephemeral data has to be deleted, and I just kill myself, and a new broker will come up. The mechanism to start brokers is only vaguely discussed, but if a host unreachable also triggers a new broker, there is a need from zero scaling property. Let's read this again. The mechanism to start brokers is vaguely discussed, but if a host unreachable also triggers a new broker, there's a need from zero scaling property. I'm not sure what from zero means here, but if a host unreachable, I guess it means if your health check finds that the host isn't reachable anymore, you start a new broker. So I guess this also means that, oh yeah, because so this is on the client, this trigger is on the client. So what he's saying here is that you can also just scale the broker to zero, meaning if there are no requests coming, the broker can just kill itself. So you could optimize it where if this group buffer is empty for too long, the broker just kills itself and there is no active broker at all. And when a client tries to write to the broker, it will try to write to this old IP, it will find that it's unreachable, and it will start the process of creating a new broker, let's say on its own node or however that works. So this is the from zero scaling thing. You can literally have like no here, meaning nothing exists, and you would scale from 0 to 1, again through the same sort of path. So that's actually pretty cool. I love this. This is really, really awesome. Yeah. And I think I only have this two. And I also have a step 5, which was mentioned somewhere here in the thread, but I think I lost it. Let me see if I can find it. They were talking about a further optimization. I think it was with Abi, but I don't remember exactly which thread. I think it was this thread maybe. Yeah, I replied here and they answered me. So here's the idea again. So somebody asks, how is the broker stateless when it's holding open connections and buffering requests in memory? Because the clients aren't act until it's committed to object storage. If the broker dies, the client simply retry. And here they ask, does this imply that posting a new job to the broker wouldn't return a response until the actual sync to S3 has gone through? Which is yes, that's what it implies. in other words, queuing a job could take 200 milliseconds for the S3 sync and plus the batch loop until the broker decides to loop. And that's how these S3 systems work. All these data infra and S3 systems, basically, they take your request, they wait for some batch to pass, and then they decide to write it to S3. And then the S3 write itself takes, let's say, 200 milliseconds. And then when all of that is done, that's your client latency. The client gets a response, that's a full latency. So the request is the batching plus the S3 latency. And Abby here says that in GCP, this means more than a second of ACK latency, which is true because you can only have one write per second in GCP per object. And the founder here, Simon, says, yeah, that's been fine for our use case. You could get this down to 100 milliseconds by sharding it into 10x q/n JSON files, but it hasn't been necessary to add the complexity. I didn't exactly understand what he meant, so I asked, well, why would it go down to 100? Your worst case is still 1,000 milliseconds in the GCS case, one write a second, but here he said very well. It's because you write to them like a ring to circumvent the one object write GCS limit. The P99 put is less than 100 milliseconds, your broker reads from out 10, and the P99 of less than 100 milliseconds to read from out 10. So what this really means is the broker would keep 10 files on rotation, and it would know, okay, if I just sent a request to object.1, for the next 1,000 milliseconds, I'll be writing to the other objects, and it will go basically at 100 millisecond steps between our objects, and in that way, you don't have to wait 1 second to write to the same object because you'll just write to another one. Now there's a trade-off here, which is that you lose the ordering. So if one object had a full ordering of the jobs, when you split it by 10, you would miss that. But again, I tried to recreate the step, and let me see how I did here. So they haven't implemented this, but it was just described here. Again, the problem is that Google enforces one write per second per object, and with a single queue.json, the hard ceiling, regardless of, there's a hard ceiling, basically. So if you shard the queue into n files, meaning our broker here has 10 files, let's say, and it goes through them in a ring-like fashion. So first it writes to queue.json, and the next request that's going to go to S3 is going to be to q1.json. So it has to maintain some sort of shard index, which is the position on that ring that it's at, and it has to maintain the e-tag per shard. This time we have a lot more e-tags because we have a lot more files, of course. It has to read from all the shards to build the full queue view. So obviously to know how many jobs are free and what you can take and what you can write and where you should write it, it has to keep all this in progress. And then it writes to one shard per group commit cycle, advancing the ring. Now, I think, again, this can have a second latency at most because if you claim a job is in progress, it lives, let's say, in Q0, .json, and then when you claim that it's completed, I think you'd probably need to write to this JSON file, unless you get more complex logic to, let's say, write the fact that this job was completed here, and then as this broker reads all of them in memory and has like the full timeline of what happened, the next time it gets to write to Q0, it will update the state with the latest one and remove the job. As you can see, this could, I think, in most cases, reduce the latency, but it becomes a lot more complicated as a result. And that's the trade-off. And you can see how these self-written things can really explode in complexity the moment you want to start optimizing performance. So I hope that these guys never have to do more than this, and they never have to implement more, because at some point, if you continue adding complexity, you get to ask yourself the question, well, is all of this complexity worth it? It's all custom complexity that we need to manage. Should I just use something like RabbitMQ? And that's why when doing something like this, it's very important to know exactly how complex do you need your thing to be, how complex is it to make it, how complex is it to operate, and how long do you think we can get away with this? I think this is so simple that they could probably get away with this for years, unless they really need some low latency thing. So I think in this example it's great. And then another thing you should think about when doing something like this is, all right, this is simple, we need it to be simple. If in 5 years we need it to be more complex, how easy would it be to migrate away? So that's again something that needs to be thought about. Some people have, for example, recommended that you use some sort of library to use a common API against all of these workers. So let's say you can adopt the RabbitMQ API or some Qs API that's literally just a wrapper on top of your simpler thing so that in the future, if you ever want to migrate away, at least the API doesn't have to change on the client. So that's a cool thing. But that's just some extra stuff. So yeah, so we're going to end with the last tweet that I have saved for all of us, which is this one. And it says, object storage is God's storage, infinite in expanse and mysterious in capability. Thanks for watching.